Howdy y'all. Today we're going to do a quick review of limiting reagents and net ionic reactions. So for limiting reagents, hopefully at this point this is starting to feel a little boring, right? Because we've done it so many times, but it's probably one of the most important things that we'll do this year. So we're given an equation. Molecular hydrogen is added with molecular nitrogen to form NH3, which is called ammonia, has a very strong smell. We need to balance the equation, so I'm going to put a 3 here, a 2 here, and now it is balanced. You should always balance your equation before you start, or always check that it's balanced. Then it tells us we add 10 grams of hydrogen to 10 grams of nitrogen. What's the first thing that you should always do? Exactly, convert everything to moles. So how do I do that? I would do 10 grams times 1 mole over the molecular weight of H2 is 2.016. So this ends up equaling 4.96 moles of hydrogen. We'll do the same thing here, 10 grams times 1 mole of molecular nitrogen, so 14.01 times 2 is 28.02 grams. If we do this, we get 0.35 moles of nitrogen, right? This is just converting grams to moles using molecular weights that you calculate from the periodic table, okay? So the first question is, how much ammonia can we make? Whenever you get a question like this and it says what products can we make? What this really is a limiting reagent problem. So you want to figure out what the limiting reagent is, right? 1, determine identity of limiting reagent, and 2, understand that the limiting reagent tells us the max amount of product produced as well as the amount of reactants required, right? We've already learned all of this stuff, so this should feel like review, okay? The limiting reagent tells us 2 things. So let's figure out what the limiting reagent is. The easiest way to do that is to convert from reactants to products. So we'll start with hydrogen. We have 4.96 moles of hydrogen. Let's convert it to ammonia, the product, by using the stoichiometric coefficients. So we do 2 moles NH3 for every 3 moles hydrogen. These numbers come from the stoichiometry. So 4.96 times 2 over 3 is 3.3. We'll do 3.31 moles of ammonia produced. Okay, we have to do it for the other one as well, the other reactant being nitrogen. So we have 0.35 moles of nitrogen times 2 moles of ammonia for every 1 mole of nitrogen. Again, we got these numbers from the stoichiometry. So 0.35 times 2 is going to be equal to approximately 0.71 moles of ammonia produced. So look, the 2 reactants result in different amounts of product being produced. The nitrogen results in a lot less ammonia produced. So the nitrogen is going to be our limiting reagent, okay? That means that this calculation up here actually doesn't happen, right? We were just seeing theoretically. What actually happens is that this much ammonia is produced. So to answer your question, or the question, right, it's this many moles, right? We also determined the limiting reagent. So then how much excess reagent is left over? Well, if nitrogen is the limiting reagent, right, that means the other thing there has to be the reagent that is in excess, meaning we have a lot more of it than we need. okay? The limiting reagent tells us two things. It tells us the maximum amount of product produced, and it tells us how much of the reactants actually react. So whenever you get a question like this, how much excess reagent's left over, how much of the thing that wasn't the limiting reagent is left over, you always start with the limiting reagent, right? It's the thing that tells basically how much everything does, how much reacts and how much is produced. So the limiting reagent we determined is nitrogen. So we have to start with that again. So 0.35 moles of nitrogen. But now, instead of figuring out how much product is made, we're trying to figure out how much of this excess is left over. So we need to figure out how much excess reacts. So we want to convert from nitrogen to that excess reagent. So 0.35 moles of nitrogen times, what did we have? We have 3 moles of hydrogen for every 1 mole of nitrogen. All this is the stoichiometry again. This is the exact same thing we did in the previous problem, except instead of converting to a product, NH3, we're just converting from a reactant to a reactant, okay? So if we do this, we get 0.35 times 3, we get 1.05 moles of nitrogen reacted. That's what this is telling us, right? When we convert from a reactant to a reactant, that tells how much reacted. So if 1.05 moles of nitrogen reacted, or sorry, shouldn't be nitrogen, it should be hydrogen. If 1.05 moles of hydrogen reacted, how much is left over? Well, how much did we start with? We started with 4.96. So 4.96 moles of hydrogen minus 1.05 moles of hydrogen equals 4.96 minus second answer leaves us with 3.91 moles of hydrogen left over, comma, unreacted. So this is how much hydrogen we started with. So hydrogen we started with. This is amount of hydrogen that reacted, right? And this is how much is left over. To figure out how much reacted, we started with the limiting reagent, which we had to figure out, and then we converted it to the excess reagent. And that tells us how much of that excess reagent reacted with the limiting reagent, okay? So let's change gears a little bit and now review a net ionic equation. How do we write that out? So here we have sodium bromide plus silver nitrate. We have the cation, the anion, we'll call this cation 1, we'll call this anion, we'll also call that anion 1. Here we have our second cation and our second anion. Remember, the first step when you're doing net ionic equations is to just switch the things, right? We don't care about any subscripts. We don't care about any stoichiometry yet. We just want to switch. So over here, we want to put cat 1 with anion 2 and cat 2 with, let's see if I can move this over here, with anion 1. So we're basically just doing a switcheroo. Okay, and what does that look like? That means we have sodium with the nitrate, and we have the silver with the bromide. And notice how I'm not worried about any numbers, right? I don't care about this 2 here. It doesn't matter yet. Nothing matters, right? Now you're like, but wait, Mr. Hicks, you brought that 3 over for the nitrate. Right, that's the formula for that polyatomic. So this counts as like 1 unit. Right, so you have to keep the polyatomics together, keep them stuck together. Okay, so then we have this sodium bromide plus silver nitrate yields sodium nitrate and silver bromide. So now you want to go onto the right side of the equation here and check the charges. You want everything to be neutral. So sodium has a +1 charge, nitrate has a -1 charge, everything looks good. Silver is +1, bromide's -1, so everything looks good. So we don't have to do anything with the subscripts. Say, for example, though, you had something like, I don't know, silver carbonate. So here, right, the silver would be +1, the carbonate would be -2. Well, that doesn't add up to be 0. So what would we have to do to make it 0? We'd have to have 2 silvers. 2 times +1 is +2 plus -2 is 0, right? That's just an example of maybe when you'd have to change the subscripts. This is the step where subscripts could change potentially, but they don't necessarily have to. So now that we've done this, the next step is to balance the whole reaction. Okay, so we see we have 2 nitrates on the left. We have to put a 2 here. Now we have 2 sodiums. We have to put a 2 here. All right, now you have 2 bromines. We have to put a 2 here. Wait, something's not right. Oh, I see. Gosh, that's embarrassing. There shouldn't be a 2 there. So, yeah, there shouldn't have been a 2 there. So then just erase that 2, scratch that out. I'll give you a second to do that. Right, and so now if we look, everything is balanced. It all looks good. You would just want to check in this step to balance the whole reaction. In this step, you would balance the ionic formulae. Right? That means like check the charges, make sure the subscript's right. So once we've balanced the whole reaction, the next thing we have to do is check the solubilities. Right? This is check solubility. Right? So you're going to use your solubility rules. If it's soluble, it'll do what? It'll dissociate. Sodium bromide is soluble. Silver nitrate is soluble. Sodium nitrate soluble. Silver bromide insoluble. Does not dissociate. So all the S's soluble, they do dissociate in water, which means they break up. So we have sodium and bromide. They broke up. They dissociated. We've got silver and nitrate. They dissociated. Here we've got sodium and nitrate. They dissociated. But the silver bromide did not. It was insoluble, which means that it was starts with a P, a precipitate. Right? Okay. Now here's Mr. Hicks's favorite part. We get to cross out the spectator ions. So if you have something on the left and something on the right, you can cross it out. I've got a sodium plus on the left. Do I have a sodium plus on the right? I do. Cross them out. I have a bromide negative on the left. Do I have a bromide negative on the right? I do not. So I can't cross anything out. I have a silver plus on the left. Do I have that on the right? I do not. I cannot cross anything out. You'll notice we have nitrates on both sides. So you can leave it like this. That's fine. I like to rewrite it. It doesn't matter how you rewrite it. I put the silver first, but it doesn't matter. And there is your net ionic equation. If it asks for your balanced molecular equation, this would be your balanced molecular equation. It's just basically the balanced equation that you have before you check your solubility rules. So this is the net ionic equation, and this is you could even say the balanced net ionic equation. And this up here would be the balanced molecular equation. And so that was a quick review of these 2 really important topics, and the worksheet that you'll do today lets you kind of work through that again. We're going to go over this in class on Wednesday before we start learning some new stuff.